Welcome. Today I am going to start that next topic, that is cycloaddition reactions. The previous class we were discussing on first type of pericyclic reactions, that is electrocyclic reactions. So previous class what we have seen that types of pericyclic reactions on the times first type of pericyclic reactions that we has discussed, that is electrocyclic reactions. And these electrocyclic reactions we have discussed that this is a unimolecular reactions. It means that one substrate is used, only one substrate or one reactant is used, one substrate is used. Okay, and what also we have discussed that in case of unimolecular reactions only HOMO is used to analyze the reactions. So here that HOMO is, that is, I can say that only HOMO is, LUMO is not used, so I can say that only HOMO frontier orbital, HOMO is used, or I can say that HOMO frontier orbitals is used to analyze the reactions. Okay, and second point is what we have seen that here we see that both heat and photochemical conditions, that the sigma bonds, that new sigma bonds can be formed, that is on con-rotatory or dis-rotatory. So that can happen by both photochemical conditions and or also by heating. So here that by both heating, that is this, and photochemical conditions, the new sigma bonds can be formed. So these are the things that we have discussed for the electrocyclic reactions that I have discussed in the previous class. Now we are going to next type of pericyclic reactions, that is cycloaddition reactions. Okay, next type of pericyclic reaction, that is cycloaddition reactions. So what is the difference between that pericyclic reactions and cycloaddition reactions? So the difference is that here, unlike that electrocyclic reaction, this is a unimolecular reactions where only one substrate is used, but that cycloaddition reactions, this is biomolecular reactions. It means that two substrates are used here. Two substrates is used. And next point is that unlike cycloaddition reactions where only HOMO frontier orbital is used to analyze the reactions, but here for the case of cycloaddition reactions, both HOMO and LUMO frontier orbitals are used to analyze the reactions. It means that here LUMO also needed to analyze the reactions. Means both HOMO and LUMOs are needed to analyze the reactions. Okay, so this is the difference between that electrocyclic reactions and cycloaddition reactions. And unlike that electrocyclic reactions where both photochemical conditions and heatings, that I mean that by both photochemical conditions and by heating, that new sigma bonds can be formed. But here for the cycloaddition reactions, here that by photochemical conditions that new sigma bonds cannot be formed. It means that here only by heating only that new sigma bonds can be formed. So here, unlike electrocyclic reactions, unlike electrocyclic reactions, here only by heating the new sigma bonds can be formed. It means that by photochemical conditions, the new sigma bond can't be formed. It means that here we only need the heat. We can't use that photochemical conditions to run to proceed the cycloaddition reactions. That means I say that we can't use photochemical conditions. Photochemical conditions for cycloaddition reactions. Why? That we will discuss while we proceed that these topics. Okay, so these are the basic difference between that electrocyclic reactions and cycloaddition reactions. Okay, now that what is the cycloaddition reactions? So if you says that for this cycloaddition reactions, so for any pericyclic reactions, the important things is the substrates. Okay, so like that electrocyclic reactions, only one substrate is needed. That substrate is like this, that it may be any that is 4 pi systems or 6 pi systems. Okay, so that things, but one substrate we are using, only by one substrate, then we are going to give heat or photochemical condition, then we are getting the reactions. But for this case, for the case of cycloaddition reactions, but that the substrates are two substrates, and the substrates is somehow like this. Okay, so it has to keep mind about of the substrates. Okay, so substrates for that cycloaddition reactions is very important. One is that I have discussed in the past class, very beginning, where I give one example of cycloaddition reactions where the two substrates are needed. The substrates are like, one is this diene. Diene means double bond, diene means two double bonds. Okay, this is diene. Okay, di stands for two and in stands for the double bonds. Okay, so diene, one substrate, and another substrate is this diene pile. Pile means lobe. Diene means that lobe the two double bonds. That is dino. Dino means that dino means that diene. Okay, and pile means which lobe the dienes. That is called that dinophiles. Pile means lobe for the dienes. So that is that these are the two substrates. Okay, that are needed. One is diene, another is dinophile. Okay, so these are the substrates for the for the cycloaddition reactions. Now we have to give the heat. Okay, that if you give the photochemical conditions, then that reactions will not proceed. Okay, we have to give the heat. Then what will happen? This will go through a cyclic transition state. It means that what things you will get, that it will move here, and this is going to move here. That I have already shown in the very beginning past class. Okay, so what that will happen, that the cyclic transition state will form. Means that is going to like this. Okay, and this has shifted So this pi bond is shifted here, so I'm showing like this, and this this double bond also shifted here. Okay, and this was there previously. Let me show that in the yellow lines, and this was there, and now that it was already there, that is this bonds, and this has shifted. It means that is going to be like this. Okay, so this is the cyclic transition state that has formed. Okay, this is the cyclic transition state. Now after this transition states, what that we see that this pericyclic reaction that proceed through a concentrated mechanism. Mechanism means that bond forms and bond break at simultaneously. That what I say, that pericyclic reactions proceeds through concentrated mechanisms. It means that bond break and bond formations occur simultaneously. Okay, the pericyclic reactions, it proceeds to a transition, a concentrated mechanism where bond formations and bond break is occur simultaneously. It means that what happened here, that this was the dienes, and here also the double bond was there. So this hello ones, that I am saying that hello dotted line represent that bond breaking, and this pink lines that pink dotted line, so that bond forming. Okay, so now what is that? This means this is breaking and this is forming, this is breaking, this is forming, this is breaking, this is forming, means simultaneously the breaking forming. Okay, so that that bond break, bond form, bond break, bond form, that type of concentrate mechanisms it follows. Okay, so now this transition state, then what happened, that then we will do this, then we will get that. So wherever that break, that I will going to break, and wherever F, that means that formations is happening. So F stands for formations and B stands for breaking. Okay, so now what I get here, this was there. Okay, so that these formations will occur here, so I will make this, and this was already there. Okay, this formations will occur, so I make that one here. Okay, and now this formation, so here F, and this is breaking, so this is break, and this is again formations, and this is again formations. So 1 2 3 2 3. Okay, so this is the final product after this. So what we seen here, that here the two substrates was there. This is that one substrates, another is this is one substrate, and this are the two substrates going to make that one product. So what we notice here, that two substrate is going to make the one product. It means that here if I says that that what I says, that thermodynamically, that means that I forgot the word, that randomness, yes. So that randomness is what that decreases. Okay, means that delta S means that S final minus S initial that is the randomness, or that finally was how much, 1, and that initially is 2. It means that that is going to minus, so delta S is getting negative. That randomness is decreases here. Randomness is decreases here. Okay, so this randomness if it decreases, so then that helps that reactions that we know that delta G, that is equal to delta H minus 3 delta S. So if that randomness is decreases, then that somehow that helps to that gives free energy delta G, means that reactions with, so for proceeding reactions we know that delta G has to be negative. Okay, so it somehow helps that reactions to proceed because the randomness is decreasing in the whole of these products. Okay, so this is what one thing we notice from here. And another thing is that if somebody is asked that whether this is endothermic reactions or whether it is exothermic reactions, so by simply looking at these reactions, that it maybe comes to our mind that since we are giving the heat, because we are giving the heat, and we know that if we are giving heat to any reactions, then that is known as the endothermic reactions, because we know that. Okay, so endothermic reactions means that heat is observed. Heat is observed is called that endothermic reactions, and another is exothermic reactions. It means that heat is released. So by simply looking at these reactions, what we see that it may be endothermic reactions, that it will come to our mind that it is endothermic reactions because heat is observed. Okay, because we are given the heat, that it observes the heat and this product has formed, so we can think that it may be endothermic reactions, but this is the wrong. It is actually the exothermic reactions. How? If you see that heat is given, just initiate the reactions. So just to proceed the reaction, just push the reactions to proceed, means just initiate the reactions, we have given the heat. But what is actually happening here, that what is seen here, that how many pi bonds were there, so that I want to make here again, that is going to be like this. This is the substrates here, this one, and this is the diene, means die means two, and two double bonds, that is called diene, and this is dienopile. Pile means law, diene means law of the two double bonds. Note that this has to be in the conjugations, the two double bonds has to be in the conjugations. Okay, another is dienopile, and this has to be two double bond should be in conjugations. Okay, now what it is forming, that it's forming these products. Now I'm not making the transition state, I'm simply making that this has formed, and what new things has formed, that one sigma bonds here form, another sigma bonds here it is formed. Okay, so from that what we seen, that 3 pi bonds, here 2 pi bonds, and here 1 pi bonds, and next that 2 sigma bonds, 2 sigma bonds plus 1 pi bonds has formed. It means that I have already discussed in the very beginning class, that this 1 pi bond cancel. It means that 2 pi bond is making the 2 sigma bonds. It means I can say here 2 pi bonds forming 2 sigma bonds. So what I have said, that this pi bonds, that I have said that is weak, and weak means they are in the high energy states. High energy states, that I have already explained, that if they are weak, it means that they are high energy states, because that electron always wants to stay in a stable state. Okay, so if electrons are in the stable state, it means that they are strong, because they do not want to go to any other state because they are already in the stable state. So that sigma bonds, since that is strong, that difficult to break, it means that electrons are in the stable state. That's why we're not able to break the bonds. Breaking bond means we want to push the electrons to some other states. Okay, so if electrons are already in the stable states, then they will not go to other states because they are already in the stable state. That's why the sigma bonds are strong bond. It means that electrons are in stable state. Okay, so now what happened that what we are doing that two pi bonds are breaking and forming the two sigma bonds. So two pi bonds are breaking and forming the two sigma bonds. It means that what we are doing here, that electrons are moving from high energy states to this stable bonds to low energy states. Okay, it means that I says that electrons are moving from high energy states to low energy state. So if I mention that diagrams, then what maybe it is happening, that this is the energy. Okay, so the reactance means that where the electrons are there and where they are moving. So what we say that if it is that like this, then this may be the pi bonds. Okay, because they are in the high energy. Okay, so this may be the pi bonds because they are in the high energy, and this is going to be the sigma bond. So I can mention that graph very clear. If the graph is like this. Okay, so now what happened here? Okay, so this is that here this is the pi bonds and this is the energy and this is the energy order. Okay, so from this pi bonds to they are moving to the sigma bonds because sigma bond is in the low energy, and this is the cyclic transition state. This is the cyclic transition state. So what we see here, that electrons from this pi bonds to moving, they will going to shift it like this, and they are going to that this sigma bonds to the low energy states. So from here what we see that just proceeding the reactions we give the heat, but after that they giving that they releasing the lot of energy and they are giving the sigma bonds. Okay, so electrons are moving from high energy states to low energy state. It means that from pi bonds to sigma bonds. So what we see these diagrams. So this diagram shows that this is the endothermic reactions. Endothermic reactions means that electrons are moving from that pi bonds means high energy states to the low energy states, means that they are releasing the energy, they are releasing the heat. It means that here what they are releasing, heat is released. Okay, so this is shows that what have you seen that this that the pericycle, that cycloaddition reactions is at exothermic reactions, not the endothermic reactions, because we seen that these pi bonds, they are from that high energies to moving to that low energy. So whenever they move to the low energy, then they will release the energy, and that energy is released in the form of heat. So that's why this is the exothermic reactions, not endothermic reactions. This is exothermic reaction, sorry, exothermic reactions, not the endothermic reactions. Here heat is given, just initiate the reactions. Okay, so heat is not observed. Heat is you have just given to initiate the reactions. After that, these reactions will proceed by itself. The reason is that electrons wants to go to the stable state. Okay, so if you just give initiate, then that electrons will go automatically and they will move from high energy states to the low energy states. So that's why that cycloaddition reactions is a exothermic reactions, not the endothermic reactions. Okay. So now next moving to that things about of the substrates, because substrate is very important for the case of any pericyclic reactions. We should understand about of the substrates. So what the substrates is here? So substrates for these pericyclic reactions are this diene, another is this is the dienophiles. This is the diene, another is dienophile. Okay, now if we what we seen that this diene, okay, here what that they used to take for that frontier orbitals, for the dienes to analyze the reactions. From this diene you used to take that HOMO. So generally I'm talking about of that, generally HOMO is taken to analyze the reactions. Okay, for the case of dienes. And for the case of dienophiles, what we say that I'm talking about of the generally LUMO is taken, because that I have said that for cycloaddition reactions both HOMO and LUMO is taken to analyze the reactions. So since they have the two substrates, so from the diene we will take that HOMO is taken, and for the dienophiles LUMO is taken. So LUMO is taken to analyze the reactions. Okay, now so if you say that if I'm talking about of that HOMO, it means that to increase that the increase the Diels Alder reactions, or sorry, yes, another types of cycloaddition reactions also known as the Diels Alder reactions. Okay, note that actually cycloaddition reactions also cycloaddition reactions actually that's I have not talked. So cycloaddition reactions that I have to discuss here. Actually we are discussing about of that cycloaddition reactions. So these cycloaddition reactions are actually two types. Okay, cycloaddition reactions we discuss about of mainly two types. One is 4+2 cycloaddition reactions. Another we will discuss, that is 2+2 cycloaddition reactions. Okay, so 4+2, what I say that this is this type of this 4+2 cycloaddition reactions. This is also known as I can say it also known as Diels Alder reactions. Okay, so 4+2 means this is that what I have discussed here, that is the substrates, this type of things. Okay, diene will be there. So why this is 4? If you take, then that is dienophiles. So this is that 2 pi bonds. So 2 pi bonds. So how many electrons are? 4 pi electrons. Okay, because this is the 2 pi bonds. 2 pi bond will give that 4 pi electrons, and this is that 1 pi bonds, that will give that 2 pi electrons, because this is 1 pi bonds. So that's why that what we say that this is 4+2 cycloaddition reaction. This is 4 and this is 2. So that they say that 4 plus 2 cycloaddition reactions. Okay, and sometimes it is also called the Diels Alder reactions. Okay, another types we will discuss that is called the 2 plus 2 cycloaddition reaction, that we will discuss after discussing on this cycloaddition reactions. So these things that I am discussing now. Okay, so this one I supposed to say very beginning, so I'm sorry. Okay, so please note that. So this here for dienes generally HOMO is taken to analyze the reactions, and for the case of LUMO, for the dienophile, LUMO is taken to analyze the reactions. And if you says that to increase the HOMO, for increase this Diels Alder reactions or 4 plus 2 cycloaddition reactions, but we needed that to increase this Diels Alder reactions, then this diene should be highly reactive. Okay, so to do this diene reactive, that is should increase that reactivity of this HOMO, and the HOMO means that highest occupied molecular orbitals. It means that we should increase the electron density, because HOMO should be high. Okay, high means that electron density should be high. So electron density will increase by the electron donating groups. It means that I can say electron donating group increase the increase the HOMO, and that means that increase the reactivity of diene. It means that it increased the Diels Alder reactions. And other case, for the case of dienophiles, where LUMO is taken to analyze the reaction, and LUMO means lowest unoccupied molecular orbital. It means that we should increase the electron density of these dienophiles. Then to increase the electron density, LUMO means lowest unoccupied molecular orbital. What I say is that the frontier orbitals, let's say this is HOMO. If I say that, let's say it here, then that case, suppose if I represent this, then that has that how many carbons? 4 carbons. So let me explain that. E and 4. Let's say this is psi 1, psi 2. Let's say this is psi 3. Let's say this is psi 4. Okay. So how many pi electrons are there? 4 pi electrons. So just fill that 1, 2, 3, and 4. Okay. And for this case of dienophiles, how many carbons are there? 4 carbons. So that for psi will be this, 2 carbons. So 2 I have to do psi 1 and psi 2, because the number of carbon atoms is equal to number of that orbitals I will draw. So I did the 2. Okay. Now that how many pi electrons are there? So 2 pi bonds means that, sorry, 1 pi bonds means that 2 pi electrons. So I will fill that 2 pi electrons. Okay. And now what do you see that for analyzing the diene case, and this is for the dienophile case. And what I see that for the diene case, what you take that HOMO. HOMO means highest molecular orbitals, which is the highest occupied molecular orbitals. So occupied molecular orbital highest, that is this one the highest. This is also occupied, but this is not highest. This is the highest. So this is the HOMO. Okay. And for the case of the dienophiles, that is the lowest unoccupied molecular orbitals. It means that this is the occupied, so we will not take, we say that unoccupied. It means that this is the lowest unoccupied molecular orbital, that is the LUMO. Okay. Now to increase this reactivity, what we say that if electrons are moving from electrons always try to move from high to low. Let's say if the energy levels, let's say if an energy levels, okay, if here and if here, that if it is the HOMO and this is the LUMO and this is the energy, Then if electrons will move from highest to lowest, then that will give the good reactions, because highest to lowest electrons from here they are moving to here. Okay, so means that this HOMO, as much as it is high energy, that is good for that, because if electrons is high, then there that amount of highly unstable, and if LUMO is low, then that amount of stability is there in this orbital. So they wants to move more interestingly to this, because this is highly stable. So that's why I say that the LUMO is generally that is unoccupied molecular, lowest unoccupied molecular orbital. So this should be that low energy states, so that this should be highly stable and electrons very likely to move to these orbitals. So to increase that dinophiles, so to increase the reactivity of dinophiles, that LUMO should be the lowest. So electron density should be very low. That means that should have that very low energy. So to means the electron density should be very less. So that is known by that electron withdrawing groups. If electron withdrawing groups are there, they will take the electrons. If they will take the electrons, means electron density will be decreases. It means that it will goes to the low energy states. So here what we say that electron withdrawing groups increases the reactivity of dinophiles. Okay, so that's what I say, that electron donating groups increase the HOMO, whereas that electron withdrawing groups increase the reactivity of dinophiles. So what we see that if in a dienes, if electron donating groups are present, then that is very good for the Diels Alder reactions, whereas for dinophiles, if electron withdrawing groups are there, then that is good for the Diels Alder reactions. Okay, now moving to that next concepts, that now moving to that on which case that the dinophiles and that dienes. Okay, so one more concept, that let's say, okay, so that's what I've discussed here. Let's say if it is the dinophiles, this is the dienes. Okay, now instead of that, diene means that electron donating groups increase the rate, that we know. But instead of electron donating groups, suppose here we have that electron withdrawing groups, here we have that electron withdrawing groups, then what will happen, that here that now we will not in this case, if in the dienes, if we have, okay, if electron withdrawing group is present in diene, instead of electron donating group, then what we will take, that here in this case LUMO is taken to analyze the reactions, instead of HOMO. Okay, so please note that if so, what that electron donating groups if present, then that is the highly reactive for the Diels Alder reaction. But instead of electron withdrawing group is present in the dienes, on that case, that here that LUMO is taken, not HOMO. Okay, the same case with the dinophiles. Okay, here that electron withdrawing group is present, on that case it is good for that this is the dinophiles. Okay, so now if electron withdrawing groups are present, then this is the good for that Diels Alder reaction. But if electron donating group is present, then same things, that HOMO is taken to analyze the reactions. That's why I told that generally for the dienes HOMO is taken. Okay, not every cases. Okay, where that will not taken, if instead of electron donating groups, if electron withdrawing group is present, on that time LUMO is taken, not HOMO. Okay, so this is the some facts about that dienes and dienophiles. Now the question is that the rate of the dienes and dienophiles. Now if you take that rate for dienes and dienophiles, so if you have that things, I think it will more clear if you discuss with the examples. So that is taken by taking the examples. Okay, for cycle addition reactions, rate of dienophiles. So what I said that for dienophiles, electron withdrawing groups increase the rate for the rate of dienophiles for Diels Alder reactions or 4+2 cycle addition reaction. Okay, so for that, what we said that if for the dienophiles electron withdrawing group is present, and that increase the rate. It means in this questions what we have seen that this is the electron withdrawing groups, 4 electron group, here 2 electron withdrawing groups, here 1 electron withdrawing groups, here no electron withdrawing groups are present. This is the electron withdrawing groups. These are the electron withdrawing groups. Here 4, here 2, here 1 electron withdrawing groups. So that dienophiles, the rate will be that electron withdrawing groups increases the rate. Okay, the rate of reactivity of dienophiles. Okay, so that rate will be going to be that first will be we have that D, then we will have C, then we will have B, then we have the A. Okay, similarly this type of dienes also very good, because sorry, here that double bond is there. Okay, so this is the dienophiles. So this double bond is in the conjugations. Here also it is observed by this, and here also it is taken by this. So this double bonds is taken, electron density is withdrawn from the both sides. So this is very reactivity. So this type of structures of dienophile is there. This is the dienophile case. Then that will going to give a good Diels Alder reactions. Here this dienophiles, that electron density is observed from here. So this is very less available. So this is also very good dienophiles. Similarly here also this electron density is observed by here or here. So this is also very good dienophiles. So, or this case also. Okay, so this diene is very good for the Diels Alder reaction. This type of dienophiles are there. Dienophiles, not diene. Okay, dienophiles, they are good for Diels Alder reactions. Diels Alder reactions. Now, next questions. If I talk about of that diene case. So diene case, that electron dominating group is okay, but with that one more factor is needed, that is S cistoids and S transtoids. So what do you mean by S cistoids and S transtoids? So let's say if this type of groups are there, okay, and this is called the S cistoid, and another is that, let's say that this is going to be like this. This is called that S transtoid. So maybe the spelling is maybe wrong, so please don't look that. So S cistoid, S stands for that this single bonds. Okay, S stands for the single bonds. So now what we say that this is the single bonds that it represents. This is the single bonds here. So that's that single bond cistoids or single bond transtoid. So these factors of that S cistoids and S transtoid is very important for the case of dienes. So what it says that if that it is a S cistoids, okay, that I if it is a S cistoids, it means that is like this. Okay, and another is S transtoid, that it means that is like this. Okay, so for this case what happened that if this is S cistoids, and if we have that, this is the diene case I'm talking about of that, this is also diene. Now we have the dienophiles here. Let's say we have, this is the dienophiles. Here also we have the dienophiles. Now if we draw that orbitals, for this case, orbitals are like this. Orbitals are like this. And here orbitals are like this. Here also orbital is like this. So what we see that here, that good interactions will occur with that. Okay, that good interactions will possible. But in this case, that is going to be like this, and this is going to be like this, and it is going to be like this. So that interactions will not so good, because they has to do the interactions with this. So that distance is high, and that there should not so good interactions. Actually, if I draw that one like that, I can draw here. So here what you see that here if we have this type of bonds here, and here if we have this, okay, so they have that interactions with this. Okay, for the case of this is that S cystidyl, and this is that S cystidyl diene, and this is the dienophile. But for the case of trans cystidyls, what you see that this thing is there. So here that it is here. Okay. Now the interactions is from here to here. It means that it is here that it has that good interactions. Good interactions is present here, also good interactions. But here not so good interactions. But here good interactions. It means that what we see that this will show that Diels Alder reactions. Diels Alder reactions occur here, but here that no Diels Alder reactions. Reason is that there is no good interaction, so no Diels Alder reactions. So that is that although for the dienes that electron donating group is present, then that will react with that one more factors that depend on that this cystidyls or trans cystidyls, means the orientations of the dienes. Okay, if it is S cystidyls, then that will give that Diels Alder reaction, but if it is transdyl, that will not give the Diels Alder reactions. I can write here that trans, that is S transdyl, not give Diels Alder reactions. Okay, so that we will discuss the examples here. Okay, so for this examples that we were discussing. Okay, so that's what that says, that here which of the following will undergo the Diels Alder reactions. So for the rate of dienes, what we will look rate of dienes, what we will look first is that should be that S cystidyls, and second is that electron donating groups increase the rate of dienes. Okay, so S cystidyl, first is that diene should be S cystidyls. Okay, and second is that electron donating group should be present. So this that the two things that rate of diens depends. Okay, rate of diens depends on these two factors. Okay, one is diens would be acidols, another electron donating groups would be present. So for this looking these two factors, here we will do the examples. So which among the following diens will undergo Diels Alder reactions? So if you look these examples, so this is say that this is in the ring. Okay, so this is in the cisadoids, but this is S cisadoids, but this is the S transidoid, because this is, although this is the single bond, rotation is possible, but this is the ring. This is cannot be do the rotation, so this will never go that Diels Alder reactions. Okay, this also go the Diels Alder reactions, this also go the reactions. And one more thing, that these groups, this will what that this is that single bond through rotation is possible, but if it will go to, suppose if I write like this, here T butyls, here T butyls, then that here that too much that bulky will happen. This is because this is the bulky groups, so too much what that says that repulsions, so this is convert into the trans, means this is always present in the transitional, so this also not to the that Diels Alder reactions, because this is the due to the bulky groups presence, but this will do the Diels Alder reactions. This we say that here that is there, so that I can explain here. Let's so always remember that if the groups are like this, okay, if that is there, here any groups is present over here, let's say the groups are present over here. So groups here may be bulky group or any group present here or here. Okay, bulky group or any group is present, so they only this position groups, means this position group, they only helps, they that I can say that they do not play a role in repulsion region, because they are in the maximum distance, because they are in at maximum distance. At maximum distance. So note that if the groups are present over here or over here, then they will not play in the role of repulsions. They will not do any repulsions because they are at the maximum distance. So they only do plus m, plus I, or minus m, or minus I effect only. Okay, so always note that if the groups are here or here, then always go for that, whether they are doing plus m and plus I or that. You don't look for that bulky, they are do the repulsions. Means they will not affect for the case of that S cystodol or cystodols. Means these groups not play a role in deciding S cystodoid or S transidoid. Okay, so they will not play. Okay, only the groups which are present either here or here or here or here. Okay, so this, that what I said, that this blue group here whatever the group is present. Okay, let's say x, y and z, x, y, z and m. So this blue group like x, y, z, m only play role in deciding S sinusoidal or S transoidal. Okay. So only these groups, if the groups are present over here in this part, then they only play in deciding S sinusoidal or S transoidal. But these groups will not play. They will just do the plus I or plus M or minus I or minus M effect. So now look at the examples. So that's why it is present here. So they will do the repulsions, because this group I said about of this group, this will not play. Okay, but this will play. So this is also not good, because they will actually do to repulsion, they will convert into this states. Okay, so what I said that this not play because they are in the trans state, and this will what I said that this will do the Diels Alder reaction because they are at these positions. So these positions again they will do repulsion. So this actually exists. The rotations will happen because single bond through not single bond present means rotation is possible. So whenever you see that single bonds, then the rotations is possible. So here since single bond is there, so rotations is possible. So this will rotate, and because they are the bulky group, so they will not stay in the same side, so one will repel. It means that that is actually exist like this. Okay, this will actually exist. So here we go to the test butadiene, we have to test butadiene means this is again going to be the transition S transoidal. So this again not do the Diels Alder reactions. So which will do the Diels Alder reactions? A, it will not do, C will do, and this also not do, E will do, and F also not do. Okay. Now looking to the next questions. So rate of the 4+2 cycloaddition reactions. So here if you check the rate of Diels Alder reactions, what I say that first is the S sinusoidal and sinusoidal we look. Next factor is the electron donating groups or electron withdrawing groups. So electron donating groups increase the reactivity of diene or Diels Alder reactions. Diels Alder reactions. Okay, so this is that here. This is that here. So this will do that. So that rate will going to be that. This is going to apply plus M. This is also plus M. Okay, this is minus M, and this is plus I. Okay, so that rate will be that electron donating group. So that is going to be passed with comps the B. Then we have that C. Reason is that this is that less electron activity group. So this will highly donated. Okay, and this is oxygen. Although this is also electron donating group. So because oxygen is a high electron activity group, so it will not so much release the electrons. Okay, because oxygen itself is a highly electron activity group. Since nitrogen is less electron active group than oxygen, so you can easily electron. So plus M is this is higher than this. That's why B, then C, then will comes that A. Okay, then we will have that E, then D. D is the electron withdrawing, that is minus M. So this is the rate. Okay. Now moving to the next questions. So one here that Diels Alder reactions. Sorry, the rate of dienes is inversely proportional to that what I said, that is aromatic rate. Reason that diene means that I need the 2 double bonds. I not needed 3. Okay, 2 double bonds. One should be in conjugation. Note that here only 2 not 3. Okay, only 2 double bonds would be in the conjugations. But for this case, 3 double bonds are in conjugation. So it means that for the dienes, they need the 2 double bonds. But due to that here, due to that aromatic, that all the 3 bonds are in the conjugations. It means that the 2 double bonds are not getting separated. They are all in the conjugations. So it means that here that getting of the dienes is very less because the conjugations is happening. But as soon as you increase that this aromatic rings, then that the conjugations will decreases. This means that getting the 2 double bonds will increases. So that's what you say, that aromatic character order. If I say that aromatic character order is first is A, then B, then C, then the diene will be that C, then B, then A. It means that Diels Alder reactions also order will be the C, then B, then A. Okay. And one more things. So whenever we talk about of that aromatic rings, aromatic character, what we have seen that you have that this type of benzene rings. Then we have that pyridines, and you have that thiophene, and you have that pyrrones, and you have that pyrrones. Okay, this is that benzene, this is the pyridine, and this is thiophene, and this is pyrrole, and this is pyrrole. So what you see that here, that aromatic character order, is first A, then B, then C, then this D, A, B, C, D, then E. So what is found that this only this purine will go to the Diels Alder reactions. Diels Alder reactions. This will not show the Diels Alder reactions. Not show Diels Alder reactions. So only that purine will show that Diels Alder reactions. Okay, because this aromatic character is less, so this purine only show Diels Alder reactions. Okay, so the same things here. And one more thing, that is, if the groups like this is the pyridines, but in this case of pyridines, what we have that we have given the electron groups. So due to this, what happened that this lone pair will be go to like this. So it means that the double bonds will be present for the Diels Alder reaction. So in this case, pyridine show the Diels Alder reaction. So the Diels Alder reactions. So it means that if there is a highly electron groups are there, on that case, if you get the double bonds, that if you able to separate the double bonds, 2 double bonds, and that should be the concentrations, then they will show the Diels Alder reactions. Okay, so today up to this. In next class we will discuss more. Thank you.